This problem is shown here as it appeared in an exam. You can pause to read it first. In this problem, there are several parts. There's a rigid part BCD that can pivot about point B, and there's a part AC, which represents a hydraulic cylinder. It can extend or contract. It can pivot about point A, and it's connected to BCD at the point C. And the problem is, given the cylinder extends by 50 millimeters, how do we determine the motion of the point D? This problem involves only geometry and changes in geometry. There are no forces that are relevant. The problem consists of several phases that are shown here. There's no need to understand now these phases. Some of the phases are general to this class of problems, and some are particular to the particular strategy adopted for this problem. We're going to start with the first phase, where we just consider the overall motion. So AC extends. How does that affect the D? There's a common misconception of students having to do with the orientation of AC when it extends. You can pause the video and think for a second about what happens to AC when it extends. Students often think that it remains horizontal, but if AC stayed horizontal, then the length BC would be longer. That can't happen because BCD is rigid. So AC needs to tilt while extending. How does BCD pivot? Here is a line corresponding to the original orientation of BCD. This line can tilt down or it could tilt up. So which occurs? Remember, AC is attached to BCD at C, and BC has to stay the same length. So here's AC initially, and here it is if BCD tilts down, and here's AC if BCD tilts up. Notice that AC gets longer only if BCD tilts up. So we have the overall motion. As AC extends, BCD tilts up. So now we're at the next phase. We need to identify a key quantity that will lead to the desired displacements of the point D. So we show the mechanism here again, and we show how it changes as AC extends. So we draw lines corresponding to the initial and the final positions of the members. We know the initial angle of 30 degrees of BCD. If we knew the final angle, here called gamma of BCD, then we could find the displacements because we know the length BCD. So what's a strategy for finding gamma? We almost always want to find a triangle in which the angle or length of interest appears, but which also has other lengths that we know. Here is one side that is related directly to gamma. AC is another line that we know something about. What is the third line of the triangle? AB. Since the points A and B don't move, we are likely to be able to find the angles and lengths related to the side AB. Here we redraw the triangle, and we have defined two new angles, alpha and beta. What's the strategy to get to gamma? This is a horizontal line, so the three angles here add up to 180 degrees. We can likely find the other angles. Alpha, because points A and B are fixed, and beta, because we can analyze the triangle. Note that both beta and gamma change as AC extends, but alpha doesn't. Let's start by finding the angle alpha. We can do so by defining another triangle, a right triangle. We can find the lengths of the sides of the right triangle, and then the angle alpha and the length L. Both legs can be determined by looking at the original diagram. The horizontal leg corresponds to the horizontal distance from A to C minus the horizontal distance from C back to B. The vertical leg corresponds to the vertical distance from C back to B, since AC is originally horizontal. From the two legs of the triangle, we can find the hypotenuse by Pythagorean theorem, and we can find alpha using the arctangent. Next, we turn to finding the intermediate angle beta, which is formed by the triangle ABC. Since we know all three lengths of the triangle ABC, we can find any of the angles from the law of cosines. The law of cosines includes one angle, so we write down the version that includes the angle beta. Since all the lengths are known, this can be solved for beta. Next, we find the angle gamma. We use the fact that the two angles alpha and beta are known, and that the sum of alpha and beta and gamma must equal 180 degrees, so that we can then solve that for gamma. Now with gamma, we can turn to finding the desired motions of the point D. With gamma, we now know the orientation of BCD when AC has extended, and we know that BCD was initially 30 degrees from the horizontal. We can find both the horizontal and vertical distances from B to D in both the initial and final orientations. By taking the difference in the horizontal distances, we can find how much D displaces horizontally. By taking the difference in the vertical distances, we can find how much D displaces vertically.